All right. First of all, thank you very much for hosting this competition. This is the 6th place presentation. Right, this is the agenda. First, a bit about my background. I'm a Master of Science, Computer Science student at the Free University of Berlin. I've worked as a quantitative researcher before, and I'm an active Kaggler, now Kaggle Masters, thanks to this competition. And I really love working with especially time series data and working on competitions. So yeah. So here's a quick summary of my model. It's a sequence model, mainly based on bidirectional LSTMs and attention mechanisms, transformer blocks. They're arranged in a UNet-like architecture. The model is applied to 24 hour intervals with 60-minute overlaps. And I aggregated the data into 1-minute time steps. So I basically downsampled it by a factor of 12. So I end up with 1,560 steps for each day. This makes it much more manageable, and the model don't need as much computation. And also, this works quite well because predictions need to be made on full minutes. So the seconds are always 0. So most notably, which was probably a bit more original, but I also saw it in a lot of other top scoring solutions, was a feature that detects repeating patterns or anomalies in the data in that sense. Others called it noise. And otherwise, I use mostly basic feature aggregations and a few more complex features. And in total, I've ensembled 4 very similar architectures. And if you count all the models for the different folds, you have 26 models which do the inference in the end. But these architectures are very similar. I will show them later. Right, so for the feature engineering, we have the repeat feature, which basically indicates if, because I saw that some sequence parts of the data is repeating, but I will show that in a second, how that works exactly. The minute modulo 15 was an important feature. I will also show that in a second, and I think we also have learned from the other presentations what this is. And then I used the mean and standard deviation aggregations for the NMO and the absolute difference of the angle Z within each minute. So the mean and the standard deviation is applied within each minute of this, so usually for 12 values. And then there were also a few less important features which improved the score a tiny bit, which were the mean and standard deviation of angle Z times NMO, or the HDCZA feature, which was from a paper. I note that I didn't necessarily calculate mean and standard deviation for all of these, but some combinations of these. And the minimum and the maximum of the NMO, and these were all calculated within the 1-minute aggregations, basically. This is the repeat feature. So you can see the red line indicates if the patient is awake. The black line indicates if there's a repeat in the data. So if you can find the same sequence, or at least 50 consecutive steps, which are non-trivially identical, so not all constant 0 or something like that, and you find them somewhere else in the series. And when I analyze the data, you see that almost exclusively the patient is awake during these sequences, but not always, but was like more than 99%. So by using this as a flag for the model, as a feature, this was quite helpful for the model, and it improved the score. This is the minute modulo 15 feature. I saw it in a post by Yuri, and he showed that the events are not uniformly distributed across 50-minute periods. I also saw with some further analysis that they are also not uniformly distributed for the onset and the wake-up events. So instead of doing some kind of post-processing with this information, I just passed the time step modulo 15 or the minute modulo 15 into the model as a positional encoding, which the model could just learn. So I left it to the model basically to decide what to do with this, and I didn't need to do any post-processing afterwards. For the target modeling, the model basically predicts whether an event occurs within a range of 0, 1, 3, 5, or 7 minutes of the current minute. I tried some other thresholds, but these worked quite well. So basically, these are all binary targets. So we have 10 target variables the model needs to predict within each 1 minute time step. And for that, I also use a binary cross-entropy loss. And the output is, after the model made its predictions, the output is averaged over each of the event types for onset and wake up. And like this, I obtain scores for each minute. And with a simple peak extraction algorithm, I get the final predictions for each event type. This is basically saying, while the largest prediction is larger than some threshold, I take the maximum and set all the predictions within a range of 10 minutes to 0. And I do this until there are no predictions left larger than the threshold. And then I do some small post-processing to avoid prediction for full minutes. I do this by looking at the neighboring probability, which is higher, and then I add or subtract one step to not land on a full minute. So for the model, this is the best single model I used. The other architectures, like I said, are quite similar. And the single model also achieves a quite good score. So we'll focus on that one. On the left, you can see the general flow. The series data goes in. You calculate the features like the HCCZA, and then you aggregate features like NMO, angle Z, or the absolute differences of the angle Z, and use the aggregations like standard deviation, min, max, or mean. Then you have all your features. You make predictions, and then you get all these probabilities and do the post-processing. The best single model I used, you can see on the right side, it uses the minute mod 15 positioner encoding at 2 places. I used it at 2 places to also works with 1, but I wanted to have it basically available right before there are no sequential parts in the model left anymore. So, and it also uses by-LSTM UNet and a by-LSTM block. And I will show what these are in a second. So here you can see the by-LSTM UNet, the by-LSTM block, and the transformer block. So the by-LSTM UNet is basically a UNet, but not using conv layers, rather using by-LSTM blocks, and so bidirectional LSTM blocks and a transformer block at the lowest level. And there was previously a question for another team why they used GRU in the middle. So you could also ask why I used the transformer block here. I tried it with the LSTM, and I found that it works. So I tried it with all the way LSTM, but I found it works slightly better when including the transformer at the lowest point. I generally had issues with the transformer for using only transformer for the entire sequence. I believe this was because it was very hard for the mod to learn the positional embeddings correctly. So by basically downsampling it really by a lot. So we have downsampling factor of 30 here before the transformer kicks in. It's much easier. The transformer doesn't really have to learn so many positions. So I hypothesize that this is why it works better to use a transformer here than for the entire sequence, which didn't work for me. Right. So there are 4 different variations of the architecture, which are all very similar. The difference are mostly in number of layers, neurons, or complexity. For some models, I think I didn't use the UNet at all and just used LSTMs. And then I had some weird layer for one model, which I called the sub-LSTM, which was basically a shared LSTM between different, like for each hour, I think. But this was mainly to get some variation in the model to ensemble well. The LSTM dimension ranged from somewhere from 32 to 400, and the fully connected from 64 to 1200. And each architecture was trained on 4 seeds and 6 folds, and I picked the model with the best seed for each fold and architecture combination. So training with all seeds, I end up with 98 total training runs, and I finally, basically after taking the best seeds, I obtained 26 models. And here's some training details. I used TensorFlow for the training of all the models. I trained on one A6000 GPU with 48 gigabytes of VRAM, and the training time was in total, if you train all the seeds, was probably around 60 hours. Didn't track it exactly, but roughly around that. And so to obtain only the models that is finally used, which are finally used in prediction, you take around 10 hours because you don't need to train on all the seeds, and the training can be stopped early at the best epoch. And now, when trying to create a simple model, you can do that. So for training on all the data, so one-fold all data with the architecture I showcased earlier, you can get a private leaderboard score of 0.831, which would have placed 8th. So this is much simpler to train, only 30 minutes on one A6000 GPU. And for the features, I did a comparison by training on one-fold of my 6-fold cross-validation with a full feature set and with only the most important features. And you can see that the improvement was really, really tiny. So 0.829 versus 0.828. So most of the, those are only very small returns you get, but this is, I guess, what you have to do to squeeze out a bit more in a Kaggle competition, but might not do in real production because it's not worth it and adds more complexity. Right, so now we have time for a bit of question and answers.